All right. So, okay. All right. So last time we showed that if F is a smooth map, between closed Riemannian manifolds M and N, uh, and suppose the sectional curvature of the target manifold N is non-positive, uh, then there exists, first of all, solution of the harmonic map seed flow defined for all time. With the initial condition equal to F, your given map, so del U del T is tau U, and U of x0 is Fx, correct? So first point was existence of a solution of the harmonic map seed flow starting from F and defined for all time. And the second point was there exists U infinity a smooth harmonic map from M to N and the sequence of times Tn such that UTn converges to U infinity in C2Mn as n tends to infinity for some sequence of times Tn tending to infinity. Right? So this is what we proved last time. Yes?
Yes, sir.
Okay. All right. So today what we'll show is that actually, so we have convergence of a sequence UTN to a harmonic map U infinity. Actually, we will prove the following theorem. So I don't know, just for the purposes of today's class, let me call this theorem 1, that actually the whole sequence the whole family UT converges to U infinity. So UT tends to U infinity in C2Mn. as t tends to infinity. Okay, so it's not just for a sequence of times, it's for all time large enough. Ut is close to u infinity in C2 norm. All right. Okay, so actually the harmonic map's heat flow converges. All right. Is the statement clear?
Yeah, it's clear.
Okay. Okay. So the main step is to look at the following, which is you take two homotopic maps and then apply the heat flow to them and see what happens to the homotopy. Okay. So what we want to do is look at the heat flow applied to homotopic maps. So what that means is we have FT, FS from M to N as S ranges over close 0, 1, a smooth homotopy between maps, smooth maps, F0 and F1 from M to N. Okay. And then what we do is for each S, we look at the map F sub S. We let U of XTS be the solution of, so the harmonic map's heat flow del U del T equal to tau U, right? With the initial condition, so at time 0, U of X comma 0 comma S is equal to F sub S of X. All right. Okay. So then U is a smooth map from N cross 0 infinity cross close 0, 1 into N. Okay. All right. So the picture is that suppose you have uh, your maps F naught, F1, and in between you have Fs. So you look at the images here. So say this is F naught of X, this is F1 of X, and this is Fs of X. So you have a curve here joining these points where you fix X and vary S going from 0 to 1. That gives a curve from F naught X to F1 X. Then what we're doing is we're applying the harmonic maps heat flow to each of these maps, F0, Fs, F1. So points will flow like this. Okay. All right. And what we so if I look at is say U sub t comma s of X, so this is a map from M to N, right? This is U sub ts of X is U of X ts. Okay. So then these points here will be what? This will be U sub t0. This will be U sub ts. And this point here will be U sub t1. Is this clear? Of X. Okay. Is the picture clear what we're doing?
Yes, sir.
Okay. So what we want to show is that actually if I look at the speed of the homotopy, what is the speed of the homotopy at time t? So you see the maps ut comma 0 and ut comma 1 are also homotopic, right? Via s goes to uts, right? These maps are homotopic at any time t. Yeah. So you can look at the speed of the homotopy at time t. This is the norm of del u del s, right? If I'm looking at the speed of the homotopy, I have to differentiate with respect to the parameter in the homotopy, right? So the speed of the homotopy is the norm of del u del s, right? Okay. And what we will show is that the maximum speed of the homotopy at time t which is what? This is the sup over x and m of norm del u del s xts. We will show that this is actually a monotone decreasing function of time. Okay. So this is speed at time t. So what happens is actually, if you start out with two maps which are very close, say F0 and F1, right? So suppose F0 and F1 are uniformly close. Then we can construct a homotopy whose speed is small. If F0 and F1 are close enough, then we can join each point F0 to F0 x to F1 of x by a unique length minimizing geodesic. Okay, defined on the interval 0, 1, whose speed is equal to the distance between F0 and F1, right? Yeah, you just join them by the unique length minimizing geodesic. This is unique for the 2 points close enough, all right? So you join them by that geodesic. That geodesic has speed equal to the distance between F0x and F1x, which we're assuming is uniformly small, less than epsilon. Then what we can show is that, so the initial speed at time 0 is very small. It's the distance between F0 and F1. Then if you apply the harmonic maps heat flow, the maps that you get, ut0 and ut1, the speed of the homotopy between them will also be small. Okay. So it will also be less than the distance between F0 and F1. So what is the precise statement? So it's the following proposition that for all s in 0, 1, for all x in M, for all t greater than or equal to 0, norm of del u del s of x t s, this is less than or equal to the max over x in M of del u del s of x 0s. Okay. All right. So at time 0, this is equal to the norm of del fs del s of x. Okay. So this will tell you that the maximum speed of the homotopy is monotone decreasing, right? Is this clear?
Yes, sir. Yes, sir.
Okay. So so maybe I can break this into 2 parts. And the second part is very simple. It says that the distance between u t0 and ut1, so this is defined to be the sup over x in M, the C0 distance, right? Distance between ut0x and ut1x. This is less than or equal to this initial speed of the homotopy. So the max over x in M norm del fs del s of x. Okay. All right. So that means that if your initial homotopy has a small speed, then the maps that you get from the harmonic maps heat flow, the distance between them stays controlled by the initial speed of the homotopy. Okay, so the maps that you get stay close to each other. All right. So for the proof of the first part, you let V of xts be the function half the norm of del u del s of xts whole squared. Okay, fine. So what we want to do, how will we prove this part one? What do you think we will use? What is the tool we have to prove this? How are we going to prove this? What tool have we been using so far to get bounds on geometric quantities under the evolution given by the heat flow? What tool have we been using?
Weizenbach.
Yeah, but to get estimates, what is the tool we've been using? That something stays bounded or so on. What is the tool we've been using? What is the tool we've been using? Come on, you should be able to answer this. Otherwise, you haven't been following at all the lectures. What have we been using to prove that quantities stay bounded? To say that the energy density is...
Yes.
Yeah, what? Yes? What tool have we been using? Orkojit, Utsav? What have we been using to prove that solutions stay bounded?
I mean, estimates on the solutions of the parabolic PDS.
No, but before that, to say that, say, the energy density stayed bounded or the kinetic energy stayed bounded, what were we using? Can none of you answer this? Come on.
Second order derivative is
Oh, come on. Before that, to get the first order derivative bounded, that was the key step. What did we use? And to get the kinetic energy bounded, del U, del T, what did we use to bound these? In terms of the initial values, how did we bound them?
Parabolic maximum.
Correct. Thank you. The parabolic maximum principle, the Schroeder estimate comes after. Once you've got boundedness of the first order derivatives, then the Schroeder estimates give you boundedness of higher order derivatives. But the first step is using the parabolic maximum principle. Right. Yes, do you remember this?
Yeah.
Yeah, have any of you been following the lectures at all or what? I mean, main tool is the parabolic maximum principle. So that's what we're going to use here to this function v. We're going to apply the parabolic maximum principle. So to do that, we have to compute two things. One is the Laplacian of v and the other is the time derivative of v, right? So for the Laplacian, you let EI be an orthonormal basis of TXM and let R going to gamma I of R be GLSX such that gamma I of 0 is x, and gamma I prime of 0 is EI, right? Then the Hessian of V applied to EI comma EI, this is what we need to compute in order to compute the Laplacian, right? It will be the trace of the Hessian, which is the sum over I, Hessian applied to EI comma EI. So this is equal to the second derivative along geodesics, right? So this is del squared, del R squared at R equal to 0 of half, so V of gamma I, so half norm squared of del U del S of gamma I of R TS. Okay, so this is inner product of del U del S with itself. So by metric compatibility, so first of all, if I take the first derivative, so this is del del R at R equal to 0 of the first derivative. The first derivative will be half into 2 into the inner product of d del R del U del S, right? Inner product del U del S. Okay. So the half and 2 will cancel, and this becomes by symmetry d del R of del U del S is the same as d del S of del U del R, right? Okay. So now when I apply this derivative, okay. So now when I apply this derivative, okay, wait, let me do this one step later. So let me keep this the same. Let me do this one step later. This is d del R del U del S. Okay. So when I apply del del R here, I'll get again d del R of the first term in inner product del U del S plus the first term inner product of d del R of del U del S. So that will be a norm squared, right? So this will be equal to inner product d del R at R equal to 0 of d del R of del U del S, inner product del U del S, plus the norm squared of d del R del U del S. Okay. Right? So the norm squared is non-negative, so I can say that this is greater than or equal to. Now I take this inner product. So this inner product, now I'll use the symmetry. I can interchange this d del R with this del del S. So that will give me d del R at R equal to 0 of d del S of del U del R del U del S. Okay. And now this, I can interchange the covariant derivatives by adding a curvature term, right? So this will be d del S of d del R at R equal to 0 of del U del R, right? Del U del S plus a curvature term, right? So this is d del R, d del S, this minus d del S, d del R, that will give me a curvature term R of del u del s, del u del r, right? Yeah, so I have this acting on del u del r, right? Because that's the vector field here, del u del r. And then I have inner product with del u del s. Okay. Is this all right? Yes?
Yes, sir.
Okay. So what is this d del r of del u del r? This is equal to the second derivative with respect to along the geodesic, right? It's the second covariant derivative along the geodesic, right? Of u of u of gamma I r ts, right? Now this second derivative, this is nothing but the second fundamental form of u, right? Applied to ei comma ei. Is that clear? Right? Whereas this second term, I can interchange this del u del r and del u del s, and then I pick up a minus sign. This becomes minus curvature of del u del r, del u del s, del u del r, del u del s. All right. Fine. So there's less than a minute. Let me stop this session and start a new one. Okay, so we were doing this calculation. So what can we see? So the first term becomes d del s of nabla du of ei, right? Yes? Inner product with del u del s, right? And the second term, this is a curvature term now, right? It's a sectional curvature into some norm squared of a wedge product of del u del r del u del s. So because the sectional curvature is non-positive, this term is non-positive. So I have a minus sign here. Therefore, this will be greater than or equal to this term here, right? Yes? Okay.
Yes, sir.
All right. So thus, Laplacian of V, this is equal to sum over I, Hessian V applied to ei. So that is greater than or equal to, from here, the sum over I, inner product, d del s of nabla du ei, del u del s, and this inner product is linear, bilinear, and d del s is linear. So I can take the summation inside. So then this becomes d del s of sum over I, nabla du ei, right? Yes. Now, what is this sum over I, nabla du of ei comma ei? What is this?
is the tension field of Q.
Thank you. That's right. It's the tension field of U, right? So this becomes d del s of tau s in a product with del u del s. Okay,
You mean tau U?
right? Sorry, tau u. Sorry, tau u. Thank you. Thank you. Tau u. Sorry. Thank you. Thank you. While del v del t is what? This is del t of half inner product del u del s del u del s. So by metric compatibility, this is half into 2 into inner product d del t of del u del s del u del s. And here by symmetry, I can interchange d del t and del s. This will become inner product d del s of del u del t inner product del u del s. And what is del u del t? 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 Are you there?
Yes, sir. Yes,
sir,
it's the
tau,
tension.
tau.
It's
It's the
tau of
tension
U.
field. Thank
Tau.
you. Thank you. Thank you. Thank you. Right? It's a solution to the harmonic maps heat flow. So del u del t is just tau u, right? So that's it. So we get the same term here and here. So that means that Laplacian minus del t, this applied to V. This is therefore, this Laplacian V is greater than or equal to this inner product. So this is greater than or equal to this inner product d del s tau u inner product del u del s minus the same inner product d del s tau u del s del u del s, which is 0. Okay, so the heat operator Laplacian minus del t applied to V is greater than or equal to 0. Therefore, by parabolic maximum principle, for all s in 0, 1, for all xt in m cross close 0 open infinity, v of xts, this is less than or equal to the max. The maximum value is attained at time 0, right? That's what the parabolic maximum principle says. So this is the max over x in n, v of x0s. Is this clear? This is what we wanted to prove, right? So this is half the norm squared, less than or equal to max of half the norm squared. So thus, the norm also satisfies this. So norm del u del s xts less than or equal to max over x in M norm of del fs del s of s. Is this okay? So this finishes the proof of the first part, right?
Sir,
Yes.
sir, before we proceed, sir, just can you just once again say why this shows that this norm is strictly decreasing? I mean, decreasing. This first part of the proposition, why is this?
Well, that's what it's saying, right? I mean, this says the value of the norm, the max. If I take max over x, the max in x
Hmm.
is decreasing, right? Because the value at time t is less than the value at time 0.
Hmm.
But then the value at time, whatever, t plus epsilon will also be less than the value at time
Okay.
t, right?
Right. Okay.
Because I just apply the harmonic maps heat flow starting from the value
Starting
at
at t
time.
plus
No, starting at t. Starting at
Okay.
t,
Okay.
not at t
Okay.
plus epsilon.
Okay.
Right? That
Okay.
becomes my initial value,
Mhm.
starting at t. So then the value t plus
Okay.
epsilon will be less than the value at the initial, less than the initial value, and the initial value is at time t then, right?
Okay. Yes.
Is that,
sir. Okay.
yeah, okay.
Yes. That's good. Great.
So I just changed the starting time, right? You just change the starting time, that's all.
Yes. Yes.
So you
Right.
start at a later time.
Mhm.
That's all. That's okay. All right. So, all right. So part 2 follows easily from part 1. So for any x in M, we can look at the curve S in 0, 1 maps to U of XTS. This is a curve in N joining U T 0x to U T1x. So call this curve, say, what should I call it? Gamma x comma t, right? So S in 0, 1 goes to U of XTS. Okay. So then the distance between UT0x and UT1x, this is the infimum of lengths of paths joining these 2 points. So in particular, it is less than the length of this path, right? Gamma xt. Yes.
Yes, sir.
And the length of path is the integral of the speed. So integral from 0 to 1 of norm of del u del s xts. And this speed is less than the speed at time 0, the maximum speed at time 0. So by part A, so by part 1. So this is less than the integral from 0 to 1 of max over x in M norm del fs del s of x ds, right? Okay. And that's equal to, this is a constant, you're integrating from 0 to 1. So it just gives you the value of this constant, max over x in M norm del fs del s of x. Is this clear?
Yes, sir. Yes.
Yes. So this is true. So this is by part one. This is by part one. And so this is true for all x in M. So therefore, the sup, that's the distance between ut0, ut1, is less than this same constant, max over x in M. Norm del fs del x. Okay. All right. So that finishes the proof of the proposition. Okay. So now we need just one small lemma, which I won't prove. I'll leave it to you as it's a simple exercise. So there exists an epsilon depending on the manifold n positive, such that if U is the domain, script U is the set of xy in n cross n, such that the distance between xy is less than epsilon n, then there exists a smooth map gamma from U cross 0, 1 into n. Okay. So this is of the form xy comma t, or let me call it s. Okay, s is the parameter of the homotopy. S. So this maps to gamma of x, y, s, such that for all x, y in U, the curve S in 0, 1 maps to gamma of x, y, s. This is the unique length minimizing geodesic from x to y in n. Okay. So in particular, the norm, the speed of this geodesic, so that is del del s of gamma of xys. This is equal to the distance between x and y. Okay, for all s in 0, 1 and xy in U. Okay. So is the statement clear? Yeah, so you have your manifold, and what we're saying is that there is a small constant, so that if I take any 2 points which are within distance less than this small constant epsilon n, then there is a unique geodesic joining them, length minimizing geodesic joining them. Okay, so this is x, this is y, and here a point here, this will be gamma of x, y, s. right? Okay. Yeah, and the reason why this is true is that if the distance from y to x is small enough, then less than what's called the injectivity radius of the manifold. So that is the it's precisely this quantity. It's the smallest epsilon, such that for any point in the manifold, the exponential map is sorry, it's the largest epsilon. Well, largest pointwise and smallest over. Okay, so for each point in the manifold, the exponential map is a diffeomorphism from the ball of radius epsilon onto the geodesic ball of radius epsilon. So here these two will be contained inside a geodesic ball around x. Okay. And so inside this geodesic ball, we know there is a unique geodesic from a length minimizing geodesic from x to y. Okay, so that's how we get this geodesic. And this geodesic depends smoothly on x and y. Okay. So I leave the proof for you as an exercise. Using what are called totally normal neighborhoods. Yeah. So it's just use a cover of n by totally normal neighborhoods. Okay. So we have this. And so now we can do the proof of the theorem. Okay. So we have to show that the solution ut converges to u infinity, right? So let epsilon be given. Okay. And assume that we can assume that epsilon is less than this constant, epsilon sub n. Okay. Now, by previous results, we know there is a sequence of times so that UTN converges to U infinity. So we can choose a capital T such that the distance between U capital T and U infinity is less than epsilon, right? Which is less than epsilon n. Okay. So since, is this clear? We can choose such a map, one of these maps ut, right? Yes, because we have a sequence converging to U infinity. All right.
Yes, sir.
Yes. Fine. So we can choose one such map. Then what we do is we, so let me just, let me draw you a picture of the proof. Now it's very simple. So you think of a graph where on the x-axis you have time, on the y-axis you have the space of maps, say C0 Mn, okay? And then what I have is I have my solution of the harmonic maps heat flow. So maybe this, it starts at F is U0, okay? And then it goes somewhere. Now, I have a U infinity, okay, somewhere here, right? Now, what I can do is I look at this at time capital T, right? I look at my ut here, right? So this is my u sub capital T. So u sub capital T is close to u infinity. right? So I can join these by a geodesic homotopy, right? And then I flow along the harmonic maps heat flow. I know that the distance between them is bounded by the initial speed of the homotopy, right? Which is small. So that means the distance for all time after this will stay small, right? And if I apply the harmonic maps heat flow, what will happen? If I apply the harmonic maps heat flow to a harmonic map, it just stays constant equal to the harmonic map. Whereas if I apply it to U capital T, I will get, UT plus S, right? Where S is positive. And this will be the same, right? Is it clear? So these maps will stay close together for all time after that. That will give me convergence of the whole family to U infinity. Is it clear?
Yes, sir.
Okay, so let's just write that down. So first of all, because the distance between ut and U infinity is less than epsilon, which is less than epsilon n, by the previous lemma, we can define a homotopy between, so my F naught, I'm going to take to be ut, and my F1 is going to be U infinity. All right. Okay. By putting Fs of x to be what? So this will be the unique geodesic between ut of x and U infinity of x at time s. Okay, so this is a point in n. Is this clear?
Yes, sir.
Okay, so then what is the maximum speed of this homotopy? So the max over x in m of norm del fs del s of x. This speed, as we just saw, the speed of this geodesic is the distance between the, since it's a geodesic defined on the interval 0, 1, the speed is just the distance between the starting and ending point, utx and U infinity x. Okay. So this is by hypothesis less than epsilon, right? Okay.
Yes, sir.
Yeah.
Yes.
Okay. So now let U tilde from m cross 0 infinity cross close 0, 1 to n be the solution to the harmonic maps heat flow, which solves the following. So del U tilde del T is equal to tau U tilde, right? And U tilde of x0s at time 0 for the parameter s, this is fs of x, right? Okay. Yeah.
Yes,
Okay.
sir.
Right. So then note that since U is a solution of the heat flow, U tilde will be just given by shifting the parameter, right? So U tilde of x t 0, this will be just U of x capital T plus T, right? Okay, so since U is, yeah, right. Okay. Yeah, because I mean, U tilde of xt starts from ut, right? U tilde of x0 is what? It is f0 of x. F0 of x is u of xt. All right. Is this clear?
Yes, sir.
Yeah. And secondly, since f1, which is u infinity, is harmonic, U tilde of x t1, this is going to be constant in t equal to u infinity of x, right? Because the harmonic map heat flow I mean, if U tilde of xt1 is equal to u infinity of x, then del u tilde del t at xt1. So the time derivative is 0, and this is also the same as tau of u tilde xt1, because this is tau of u infinity at x. All right. So this constant solution satisfies the harmonic map's heat flow, and we know that the solutions to the harmonic map heat flow are unique. Therefore, by uniqueness of solutions, the solution has to equal this constant solution, right? Yes?
Yes, sir.
Okay. So that's it. So we get that thus, by part 2 of the previous proposition, we get that the distance between u tilde t0 and u tilde t1, this is less than or equal to the max over x in n of norm del fs del s of x, which we know this is less than epsilon. And this distance, u tilde t0, is nothing but u sub capital T plus t, and u tilde t1 is nothing but u infinity. Okay. Right. So this implies that u sub t converges to u infinity in C0 Mn, right? It converges uniformly. Yes?
Yes.
So we got the convergence in C0. So how do we get the convergence in C2? How do we get that? Well, we know that the family UT, this is pre-compact, right? In C2Mn. Yes, because the C2 plus alpha norms are uniformly bounded for all time. Yes.
Yes,
Okay.
sir.
So since the only possible limit point in C2Mn is U infinity, because the sequence converges uniformly to U infinity. It follows that the whole family converges in C2. So UT converges to U infinity in C2Mn. Okay. Is this clear? So that finishes the proof. All right.
Yes,
Is
sir.
this, yeah? All right. Anyone, any questions? Yes, so we showed the C0 convergence, and then we use the fact that in C2, my family UT is pre-compact. So for a pre-compact family to show convergence, you just have to show that the family has a unique limit point, right?
Yes,
Then the
sir.
family converges to that limit point, right? Once you know it's pre-compact, for a pre-compact family, you to show convergence is the same as showing it has a unique limit point. Right? And here the limit point is, any limit point has to be U infinity, because in C0, UT converges to U infinity, right? So the only possible limit point is U infinity. Okay. So therefore, the whole family converges to U infinity in C2Mn. All right. Okay.
Yes, sir.
All right. Okay. Okay. So we're almost done with the course. There are just a few more things I want to talk about. So maybe I'll spend time on that today, and then the next two classes we can just do the exercises. Okay. So I want to talk a bit about uniqueness of harmonic maps. So for that, we need to look a bit at the second variation of energy. So in other words, the second derivative of the energy along a curve of smooth maps, UT. Okay. Okay, so there's less than a minute. So let me stop this session and start a new one. Okay. Okay. So let's consider the following situation. So we have M and N closed Riemannian manifolds. And let's suppose, as always, that the sectional curvature of N is non-positive. And suppose that say UT this is a smooth homotopy of maps U0 and U1, which is a geodesic homotopy. Okay, this is a smooth geodesic homotopy. So what does it mean to be a geodesic homotopy? That means that for all x in M, the curve T goes to UT of x is a geodesic in N. Okay. All right. So this is the kind of homotopy we constructed in the last theorem, right? We took a geodesic homotopy between U capital T and U infinity, right? So in general, let's just consider a given geodesic homotopy of maps. Okay. Then we want to compute the second derivative of the energy for this geodesic homotopy. Okay. So let's do that. So first of all, we have the first derivative of energy, right? So we know that ddt of energy of UT this is equal to minus integral over n of the tension field of UT with the time derivative, the variational vector field, that is del UT del T, right? Yes, we know this.
Yes, sir.
Yes? Okay. So now let's look at the second derivative, right? So d squared dt squared of energy of UT, what is this? So I have to differentiate this. So by metric compatibility, what will this be? This will be inner product of d del T of tau UT, inner product del U del T, plus there'll be another term, tau UT d del T of del UT del T. But what can we say about this last term? D del T of del UT del T. What do I know about this? What do I know about this term? My assumption is the homotopy is geodesic, right? What does that mean?
This will be 0.
This will be 0, right? Because this is the acceleration of this curve. T goes to UTX, right? So this is 0 because the homotopy is geodesic. Okay.
Yes, sir.
Okay.
Yes.
So we get a formula, right? We get a formula for the second derivative. It is minus the integral over n of inner product of d del T of tau UT del UT del T. So this doesn't help us too much unless we can see where this term d del T tau UT inner product del UT del T, where this is coming from, right? So, so we want to simplify this. Yeah. Now, if you notice, this term d del t tau u inner product del u del u del u del t. If my parameter was s, if I called it s instead of t, then this term is what comes up when I computed the Laplacian of del u del s, right? Remember this earlier theorem here. Yeah, when we computed the Laplacian of the norm squared of del u del s, then what you got is this, right? This Laplacian was greater than or equal to the inner product d del s tau u del s, right? So this is a similar term which is coming up below in this formula for the second derivative of the energy. So we should look at the Laplacian of del u del s whole squared, right? Okay. Sorry, the Laplacian of norm del u del s whole squared. Okay. So let's do that. So let's compute Laplacian of half norm squared. So instead of s, my parameter is t here, del u del t. Okay. Right. So what will this be? So, okay, so let me compute rather, instead of the Laplacian, I just do one term. So the Hessian of this applied to EI, right? Yeah, this is the computation we did earlier, similar computation. So what will this be? This will be, so it's the second derivative along a geodesic. So this is del r at r equal to 0 of the first derivative. So the first derivative will be inner product d del r. So here I look at u as a function of u of gamma I of r comma t. Okay, where gamma I is a geodesic such that gamma I prime 0 equal to EI. Okay, this is the same, essentially the same computation we did earlier. So, okay, so this is d del r of del u del t, inner product del u del t. Right. So this is going to give me two terms. The first is d del r at r equal to 0 of d del r of del u del t, inner product del u del t, plus you'll get a norm squared, right, of d del r at r equal to 0 of del u del t whole squared, right? Okay. And now this term, we know what to do. This first d del r we can interchange with this del del t, and then we'll have another d del r and del del t. Those we can interchange by adding a curvature term, right? So I'm just going to shorten steps here. This is going to become d del t of d del r at r equal to 0 of del u del r. All right. Inner product del u del t plus this. So this norm squared, this is norm of nabla EI of del u del t whole squared. And then I have a curvature term, right? So I had this d del r and d del t. I interchanged to bring the d del t first. So this is going to be a curvature term, Rn. The d del r will come second. So there'll be del u del t, del u del r at r equal to 0. And this will act on this del u del r. This will act on del u del r. Okay. And then I have del u del t. And this is at r equal to 0. Is this okay? Yes?
Yes, sir.
All right. Okay. So what is this? This is d del t. This d del r at r equal to 0 of del u del r. This is the second covariant derivative along the geodesic gamma I of r. So this is going to be, like we computed before, this will be the second fundamental form of u acting on EI. Okay. Inner product with del u del t.
Sir, in the last equality, there would be a sum over I, right?
I haven't done the sum over I yet. No. I'm just computing one term. I'm just computing the Hessian, first of all, applied to EI.
Oh, okay. All right.
Yeah, I'll do the sum just now. I'll do the sum. Okay, so then you'll get, and so this curvature term, I can interchange these two to get something which will be an actual sectional curvature. So minus sum, there's no sum. So minus inner product Rn. So del u del t. Sorry, no, I'll change this del u del r. What is del u del r? That will be du of EI, dut of EI, del u del t, dut of EI, inner product del u del t. Okay, so thus, when I take the sum, so I'll get the Laplacian of half norm del u del t whole square is equal to, so here when I take the sum of the second fundamental form, I'll get the trace of the second fundamental form, which is the tension field. So that will give me this term which I want, d del t of tau ut, inner product del u t del t, plus I'll get the sum over I of nabla EI of del u del t whole square. This I can write as just the norm of nabla del u del t whole square. Okay. Fine. And then I'll have minus the sum over I, inner product Rn dut EI del u del t dut EI del u del t. Okay. So thus d squared dt squared of energy of ut, this is the integral over n of minus inner product d del t tau ut del ut del t and this minus this inner product d del t tau u del t, is this term here. This term, if I take it to the other side, it becomes a minus, and I take this Laplacian to this side. So then what will I get? I'll get this is equal to integral over n of minus the Laplacian of half norm del u del t squared, right? Okay. And then I'll have plus these other two terms, plus norm of nabla del u del t whole squared minus sum over I inner product Rn dut ei del u del t dut ei del u del t. Okay. Then dvol. Is this all right? So the Laplacian term, integral of the Laplacian will be 0, right? By the divergence theorem, because the boundary of M is empty. Okay. So thus we get theorem for a geodesic homotopy So let me put it in two parts. One, for a geodesic homotopy, d squared dt squared of energy of ut. So for a geodesic homotopy ut, the second derivative of the energy, this Laplacian term disappears. You just get these two terms, integral over n, norm nabla del u del t whole squared minus sum over I of these sectional curvature terms, Rn of dut ei del u del t dut ei del u del t dvol. Okay, so this implies immediately if the sectional curvature of n is non-positive, then you can see from the above that the second derivative of the energy along a geodesic homotopy is greater than or equal to 0. So that means the energy is convex along geodesic homotopies when the target has non-positive sectional curvature. So thus, energy is convex along geodesic homotopies. Is this clear? Okay, this is true if the sectional curvature is non-positive. All right. Yes.
Yes, sir.
Okay. So as a corollary, we get that. So let me assume one lemma. You can find the proof of this in the notes. So M and N are closed Riemannian manifolds. And suppose the sectional curvature is non-positive. So if Fg from M to N are continuous, well, okay, fine. Let me just take smooth homotopic maps. Then there is a smooth geodesic homotopy between F and G. Okay. So I won't do the proof of this. But it's saying if there is a continuous homotopy, then I can upgrade that homotopy to a geodesic homotopy. Is it clear? Okay. All right.
Yes, sir.
Okay, fine. So let me assume this lemma. So then we can prove proposition. So again, Mn closed Riemannian manifolds, sectional curvature of M non-positive. Then if F from M to N is a harmonic map, then F has minimum energy in its homotopy class. So the energy of F is the infimum over G. So smooth maps from M to N such that G is homotopic to F, energy of G. Okay, so F has minimum energy in its homotopy class. Okay, so this is initially what we started out by wanting to do, right? Which is find maps of minimum energy, right? Right when we started looking at harmonic maps, our motivation for defining harmonic maps was that if we had a minimizer of the energy, it would have to be a harmonic map, right?
Yes.
Yeah. And now we're seeing that if I take closed Riemannian manifolds where the target has non-positive sectional curvature, the key point here is non-positive sectional curvature, then any harmonic map has minimum energy in its homotopy class. Yeah. So, for example, any geodesic So let me take it from S1 to N. Any closed geodesic, sorry, not just a geodesic. So any closed geodesic. So that I can think of as a harmonic map from S1 into N, right? Yes?
Yes, sir.
Yeah. So this has minimum energy in its homotopy class. And for geodesics, we know that length squared is equal to proportional to energy. So that will tell you that in fact this has minimum length in its homotopy class also. So minimum energy in its homotopy class. And hence minimum length in its homotopy class. Okay. All right.
Yes, sir.
Yeah, because remember, for any gamma from S1, which I think of as 0, 1 modulo identifications, where you identify 0 to 1. What is the length of gamma whole squared? This is integral from 0 to 1 of norm. One second. No. Sorry, wait. It will have minimum energy. This is an argument we've done before. One second. I'm just getting this wrong. One second. See, okay. So we can assume that one second. So sorry, I didn't want to get stuck on this. So one second, let me just see. So we have the energy of gamma naught. This is less than or equal to the energy of gamma. Right. From this, I want to get that the lengths are less than or equal also. So what is the energy of gamma naught? This is integral 0 to 1 norm gamma naught prime squared dt. And gamma naught, norm gamma naught prime is constant. So this is just equal to norm gamma naught prime squared, which is equal to the length squared, right? Yes?
Yes.
Okay, so this is okay. And this is all right. So the length squared is less than the energy of gamma. Yeah, well, if I assume, see, length is invariant under reparameterizations, right? So, yeah, so so if I reparameterize to have constant speed, right? If I reparameterize to have unit speed,
Yes.
so reparameterize, yeah. So if I reparameterize, the energy is not invariant under reparameterization. So let me just see 1 second. This is integral 0 to 1 of norm gamma prime squared. Yeah, so okay. No, I'm being stupid. So we can always assume gamma is of unit speed. Sorry, of constant speed. In which case the energy is equal to the length squared. I think this is okay. Yeah. Yeah, so the picture is something like this. In non-positive curvature, if you have a closed geodesic, it will be shortest length in its homotopy class. So all these other curves will be of larger length. Yeah, see, since the length is invariant under reparameterization, if I take a closed curve, right, then I can always reparameterize it so that it has constant speed, right, on the same interval. Yes, that I can do. Yeah,
Yes, sir.
Yes, sir.
right. So I can always assume that my curve is constant speed, and then I get this. Okay, sorry, I ran out of time. Can we just do 5 minutes and I'll finish the proof of
So,
this theorem here that the
sir, then you
yeah,
have
can
to,
we use another
yeah,
meeting?
sir, you have to join from the first link or the second link. You can
Yeah,
join.
let's join from the first link.
Okay.
Yeah, can we do that?
Yes, sir.
So I'll just take 5 minutes to
Yes.
finish this. Yeah. Okay. This proposition and one more corollary, and that's it. Yeah. Okay, so let me stop this and we'll join from the first link then. Okay, there are 3 links. Join from the first one. Okay. So yeah, I'm stopping this. We'll join from the first link. Okay. Thank you. Okay. So yeah, so if we have a harmonic map where the sectional curvature of the target is non-positive, we want to show that it has minimum energy, right, in its homotopy class. So the proof is given G smooth map such that G is homotopic to F, right? By the lemma, we can choose a smooth geodesic homotopy UT T in 0, 1 from F to G, right? So then what can we do? So I want to show that energy of G is greater than or equal to energy F. How do I do this? Yes, what do we do? Orkojit, Utsav, how do we show this? Are you there?
Yes, sir.
Yes, sir, I'm there thinking.
Oh, it's just a one-line proof. The one variable calculus. Okay, so since F is harmonic, so okay, so let what? Yeah, okay. So let me define a function phi of t, which is energy of ut. Okay, fine. Then F harmonic implies that phi prime 0, which is ddt at t equal to 0 of energy of ut, this is 0, right?
Yes,
For a harmonic map, we know that the first variation of energy is 0, right? So phi prime is 0, then what can you do? Well, sectional curvature is non-positive. What does this imply about phi?
convexity
Phi is
we have.
convex. Yeah.
So then what?
Oh, then we can't have like those. If it has another zero, then it will be identically zero, that thing.
Well, just say it simply. Look, phi prime 0 is 0, phi double prime is greater than or equal to 0. এটা যদি একটা ক্লাস 12 এর বাচ্চাকে জিজ্ঞেস করতাম কি বলতো?
আচ্ছা, ওখানে
Phi
মিনিমামটা অ্যাটেন্ড
prime
হবে
of
স্যার।
আরে বাবা, phi prime of t is greater than or equal to phi prime of
হ্যাঁ
0
হ্যাঁ
তো, which is equal to 0. তাহলে তো হ্যাঁ, তো phi prime is greater than or equal to 0 for all t. That means phi 0 less than or equal to phi 1. ব্যাস হয়ে গেল। ঠিক আছে?
Yes.
Yes, sir.
এটা ক্লাস 12 এর বাচ্চা করতে পারত, তাই তো? Okay, done. So that proves the minimum in each homotopy class. Okay. And then we have finally a theorem. So I'm just writing sectional curvature non-positive. So and I take ut t in 0, 1 geodesic homotopy. Right. So then if u0 and u1 are harmonic, right, then then in fact ut is harmonic for all t 0, 1, and the energy is constant along the homotopy. Energy of ut is equal to energy of u0 for all t. Also Yeah. So. So maybe I should write this as 1. Okay, no, I'll do the rest next time. So let me just do this. Okay, fine. So this proof is just a couple of lines. So proof, what do we do here?
From the above lemma, we have that this energy relation inequality, and then since U0 and U1 both are harmonic, so both are minimized.
Right.
So get like all of them are equal, so all of them are harmonic.
Yeah. Okay. So let phi t again be this energy of ut. Yeah. So then phi prime 0 is equal to 0 and also phi prime 1, right? Yes. And phi prime is increasing. Yes, because
Yes.
phi double prime is greater than or equal to 0. So if it's an increasing function which takes the value 0 at 0 and 1, then it must be constant equal to 0, right?
Right.
Yes.
So that implies that phi t is constant. And that implies that for all t in 0, 1, energy of ut, this is equal to energy of u0, which is to the infimum over g homotropic to u0 of energy of u0. This we showed in the previous proposition, right? This is the minimum in the homotropic class. So this is also the minimum in the homotropic class of ut itself, right? Because u0 and ut are homotropic.
Right.
Sorry, this would be energy of G. Yeah. So that means ut has minimum homotopy, minimum energy in its homotopy class, right?
Mhm.
And that implies that it is harmonic, right? Because thus ddt of energy of ut epsilon, sorry, dt epsilon at epsilon equal to 0. This is 0 for all variations ut epsilon of ut.
Okay.
And that implies that ut epsilon, ut is harmonic, right?
Right. Yes.
So that's it. Okay. All right. So let's stop today and we'll continue on Friday. Any questions? Is this okay?
Yes, sir.
Yeah, remember a map is harmonic if and only if the first variation of
0.
energy is 0 for all variations.
Right.
That's it. Yeah, that's it. So, okay.
Mm.
Okay, let's stop and we'll continue on Friday. Okay, thank you.
Okay.